Good morning. I'm Altaf Hussain, former professor, Department of Chemistry, University of Dhaka, Bangladesh. We were recording lecture series on X-ray crystallography and solid-state chemistry, following a syllabus of one of the universities of Bangladesh. This is the 14th lecture, which will be given today. In the 13th lecture, I talked about the reciprocal lattice and the relation between direct lattice and reciprocal lattice, which is very important for the crystal structure determination. So the next slide this is the slide, and we are talking about Bragg's law in reciprocal space. It is a very important property in reciprocal lattice. Is a simple visualization of Bragg's law. And what we have to do now, well, let us consider a crystal in X-ray beam with wavelength lambda. If we assume the crystal is oriented so that the X-ray beam is parallel to a plane, in this case A star and C star plane. And if we draw a line on XO, that is the XO, in the direction of the beam passing through the reciprocal lattice origin O, and we draw a circle with a radius of 1 over lambda and its center in C. XO is located so that O falls in the circumference. We have now to look into the properties of an reciprocal lattice point lying on the circle. We can see a reciprocal line on the circle and the point is P. So the angle OPB is inscribed in a semicircle, and thus this is a right angle. Is it not? And therefore sine OPB is equal to sine theta, as this is theta, sine theta, and sine theta, which you can find out from this, it will be OP, that is OP by OB. So from there we can find out sine theta and find this relation, and you can see we come up with a Bragg equation, and that is a direct visualization of Bragg equation using a reciprocal lattice construction. In the figure we are showing this reciprocal lattice construction as well as direct plane and the reflected ray in this B. This construction is not limited only for AC section. It holds good for other reciprocal lattice points too, and that we can get from rotating this circle about the diameter OB, and the figure so generated is a sphere, and that sphere we call a sphere of reflection. Thus, any point on the surface of this sphere, same condition holds as for P. So this fulfills the Bragg reflection, and that one what we use very much in determining the X-ray crystal structure. Next one that you see, we talked about sphere of reflection. So with the if it is a direct axis, and here are the sphere of reflections, This is a sphere of reflection, and this sphere of reflection depends on lambda. That is, if we have a wavelength, shorter wavelength, the sphere of reflection is bigger, and the longer wavelength, the sphere of reflections becomes smaller. So sphere of reflections in two wavelengths, we are showing, we see it here. And here we can see the sphere of reflection and reciprocal lattices of two wavelengths. If it is shorter wavelength, then we have compressed reciprocal lattice points. If it is longer wavelength, we have enlarged reciprocal lattice point, which you can see here. Next slide. Well, this slide it tells about a little bit of the number of possible reflections, which is n. We can get it by these equations, the number of reflection, 4 by 3 pi into 2 by lambda cube divided by volume of reciprocal cell. So we can get it from volume of reciprocal cells as well as volume of direct cell too, number of reciprocal lattice points within the limiting sphere. As the sphere grows, the number of reflections can be also observed more. If there is only one, let's say only one point per reciprocal cell, the total number of reciprocal possible reflections can be calculated approximately. For example, let's take an example of a crystal which is a unit cell 20 angstrom. A is equal to 20 angstrom, B is equal to 10 angstrom, and C is equal to 8 angstrom. And if it is a rectangular one, orthorhombic we say it, and then the volume is 1600 angstrom cube. If we take the copper radiation, that is 1.5418 angstrom, and put it here and get the direct cell volume, and therefore we can get the number of possible reflections, and that becomes 14,600 reflections for this particular example. If we just take a shorter wavelength, say molybdenum K alpha, lambda is 0.7107, and the possible reflections we can get about 100, almost 150,000. So this is a huge number of reflections, but well, we should not to worry about it. All reflections are not unique reflections, and therefore when we measure, we according to the crystal structure and symmetry, we can reduce this data, which we will talk when we talk about single crystal data reduction. Well, this slide I just showed you that we were talking for last couple of lectures about the section 4 of the syllabus of the university, which we took as an example and preparing the lecture. So in that fourth section, we were talking X-ray. It was says the X-ray, generation of X-ray, properties of X-ray, X-ray filter, diffraction of X-ray, etc. And you can see here all these points and maybe a little bit more points we have covered in last 4 or 5 lectures of section 4 of the syllabus. Now the section 5, which is powder diffraction techniques, that's what we have to start. And from this lecture we might need another 3-4 lectures to talk about powder diffraction techniques. What is the content of the syllabus? The powder method, principle and uses, the device sharer powder camera, linear focusing camera, the powder diffractometer, comparison of diffractometer with film methods, high temperature powder diffraction, effect of crystal size on the powdered pattern, measurement of D values, refinement of unit cell parameters, indexing of powder patterns, structure determination from powder patterns. These are the content of the syllabus which we are following to discuss in the powder diffraction techniques. To start now, the powder diffraction techniques, well, this is what is the very old one, that means during the early days, very early days, when we see that the X-ray diffraction technique is being used in characterizing solid materials. The two scientists devised camera independently. They are Dewey and Scherer from Germany in 1916 and Hall in 1917. The technique is very simple technique, and that is the beginning of crystal structure determination of crystalline powder samples. What we did, we irradiate a crystalline materials by a monochromatic X-ray. Monochromatic, it could be nearly monochromatic, may not be purely monochromatic, but nowadays we do use purely monochromatic. At that time, nearly monochromatic, I say. And recording these diffracted cones, we will talk about these cones reflected on photographic film. And in this top of here, you can see the schematic diagram of a Dewey-Scherer X-ray powder camera. Here is the metallic unit or metallic which is light proof. Lead should be light proof. A collimator, here is a collimator by which we pass the X-ray, and there is another collimator which beam stop, and we have a sample holder here. Here is the sample holder and a magnetic disc to rotate this sample holder so that various diffraction angle we can cover. And then there is film over this camera, this film, and to clip to tighten the film in the circumference of camera. This is a schematic diagram also. So that's what we have talked about. What are the important element we have in the camera, and then we go to see how a camera looks like. This is the Dewey-Scherer camera, and here what I talked about, it's a light proof metal disc, and then this is a metal camera, and here we talked about the X-ray beam coming in by a collimator, and this is a beam stop collimator again, and there is the motor by which you are rotating it. So the key points about the Dewey-Scherer camera, we do have to have a powder sample. So the sample is prepared in fine powder, and then mount this sample in this sample holder here, and we have a motor by which we rotate continuously the sample holder so that we get Bragg equation fulfilled in various planes of the crystals. So we have an X-ray beam. We said that monochromatic X-ray beam is required, direct onto the sample. We talked about monochromatic X-ray beam in our earlier lectures. So it should be a monochromatic X-ray beam. And then we get diffraction cones. What do you see? What we mean by diffraction cones? We have X-ray beam coming here. Here is a sample, and then if some diffracted rays are coming up here, and that diffracted X-ray, which is recorded in the films, and it looks like a cone, and that what we call diffracted cones. So what we do when the X-ray hit the crystal lattice, the direct at the specific angle based on the Bragg law and creating cones of diffracted radiation. That is what it is. So we do get, see if we disassemble the forward reflections and backward reflections. So the cones looks like this. And then after getting this diffraction cones in the film, what we have to do, we have to analyze it. And then how do you analyze this? First of all, we have to develop the film and then dry it, and then analyze the diffraction cones length, which will in the next slide. The position and intensities of the diffraction rings are measured and analyzed to determine the crystal structure, including lattice parameters and crystal size. What are the important consideration we have to do? We have to make the sample rotation with the speed to further improve the randomness of the crystal orientation. The sample is often rotated while being irradiated. Film development, we should have an exposure time depending on the type of materials, size, and what are in the materials, the type of metals, etc. So depending on these, we have to set an exposure time and then develop the film for visualization of the pattern. Well, this is the early camera, device share camera, but then we do have many different advancement on this camera, and you will see that there are different types of film loading types, and with this we can see the intensity better, resolutions better, etc. So we go to the next slide, and you see here we are talking about the how do you mount the films in the camera. There are different methods to mount the film in the camera. So here you see, this is, if we remember, this is how the X-ray beam is going through the collimator, and beam stop is here, and here is the sample, and then our film is like this. So we get two holes for the beam stop and incident beam, and then if we flatten the film, we get the cones, pair of cones like this, and this method is called Straumann's method. And what we do, we always use Straumann's method. I would say maximum people are using this technique, film techniques, Straumann's technique to mount the film. Okay, there are other technique, Bardley technique, Van Arkel technique, Bardley Bragg techniques of mounting films. So now, as we see that here it is a device share method with Straumann's methods of film mounting. We are showing you here the perspective view, film laid out flat, and then a geometry of device share method. And that's what I'm discussing a little bit here. In the left shows the formation of diffraction cones. We were talking about diffraction cones, and this film shows the formation of diffraction cones. Mind it is Straumann's methods of mounting the film in the camera. Okay, and then figure 2, it's this film. When we flatten it out, we see the pairs of cone, diffraction cone, backward reflection. Okay, and if this pairs of cone has a distance s, we can relate it mathematically with theta, and thereby we get the per millimeter of theta, per millimeter of film subtended angle we can find out. So how we do it? Arc by angle. arc is this one by angle, which is arc is S, and this arc S is equal to phi, and therefore S by phi, and this S phi is obviously we can see it's 4 theta. From here we can find out the S is equal to 4 theta. How it is? Because if we take the device camera and having the diameter 11.46 centimeter, you might say, why this 11.46 centimeter? It's a simple mathematical relation, and this 11.46 diameter of camera, we see that 1 millimeter of film subtends an angle of 1 degree. So S is equal to 4 theta, and from here we can find the theta. And from theta we can convert it into d, that is interplanar distance of family of planes. That's a little bit better view of the X-ray beam hitting the sample, and then beam stop, and then the cone, forward cone, backward cone, and here the film, we flatten the film, here it is. And this is what is 2 theta is equal to 0, and this is 2 theta, here is 180 degrees, 180 degrees. Well, next we can see some film of device sharer powder method. The A is a copper. We get the pairs of diffraction cones here. This is the different cones pairs, and each one is copper. And the second one B is a tungsten. This is a tungsten, body center tungsten, and the third one zinc. All metal are being irradiated by X-rays, and we get this film stack. You see, every one is unique in its character. So it is said powder pattern is the fingerprint of solids. Okay, with this we stop here, and we will take more techniques like linear camera and diffractometer. How we deal with, we will take the principle and working principle of linear camera, as well as linear focusing camera plus diffractometer. Nowadays, very little, I would say most of the laboratories, they are taking powder by diffractometer, not going through this device sharer camera or even not linear camera. But we will talk this linear camera and a principle of diffractometer in the next lecture. Thank you very much.